Let's let u equal the vector 2, 1, and v equal the vector 1, 4. Find u plus v. Now, if you wanted to, you could assume that u is at the origin, the tail anyway. But here, when you're talking about addition or subtraction of vectors, that's not necessary. So I'm just going to pick a random spot to draw u, and then I'll show you how to visually add v, and then I'll show you what it means symbolically, and it actually won't take that long. So let's just start, for the sake of argument, let's start with the tail of u right here, and it's at the point 2, 1, but I don't even care. Doesn't even matter. And so you treat the tail of u when you're drawing the vector, wherever it's at, you treat that like the origin. So you're going to go from that tail, you're going to go right 2 and up 1. So does that make sense how I got my visual representation of u? And again, I picked that tail randomly. If I had started over here, I would have gone from that tail over 2 up 1, and it would have been an equivalent vector, just a copy of the other vector, right? So forces add vectorially, so do velocities and other quantities add vectorially. So here's what I mean by adding vectorially. So you take the vector u, if you want to represent it using a picture, which is the vector 2, 1, I'll put that right here. And on its tip, which is where the arrow is, right, where this part of the arrow is, on its tip, you make that the tail of v, the thing you're adding on. So let me do that in blue. Now let me do it in red so it shows up better. And then, so that's the tail of v, and then I'm going to draw v in. So what do I do from that red point? So where do I go? Right 1 and up 4. So over 1 and up 1, 2, 3, 4. And that's going to be the tip of v, like so. And then it turns out you get u plus v by drawing an arrow from the tail of u to the tip of v. So look at the vector in green, look at its beginning point, the tail, and draw an arrow from that to the tip of the vector in red. And that is u plus v, everyone. So the vector in blue is u plus v. And that is how we add vectors using the triangle law. There's also a parallelogram law, and where u plus v turns out to be one of the diagonals of a corresponding parallelogram, but we're not going to worry about that here. The triangle law is good enough for most purposes. So that's how it's done, and that's how, for instance, forces, if you represent a force by the length of the vector, so that's weird, like a force in pounds would be represented by the length of the arrow. But it actually works out quite well in modeling real-life situations where if you use arrows, and the length of arrows represents the amount of force, so the longer the arrow, the more force. It turns out that forces applied to an object at different angles add vectorially. Imagine two people kicking a soccer ball at the same time. One person from over here, one person from over here. Where does the ball go, right? That sort of thing. Now, let's say we wanted to take u and subtract v. Oh, so I guess I can, well, let me use one down here. Let me draw another one down here. Let me draw u again. So I'm going to make my tail right here and go over 2, up 1. So there's another copy of u, and I'll do the subtraction on this guy. Now, we know the component form of v, so what is negative v? Negative v is, it's just what you think it is. It's negative 1, a scalar of negative 1 times v, which would be negative 1, negative 4. So all I have to do is think of u minus v as u plus a negative v and use the triangle law once again to do that addition. And that'll be u minus v. So, okay, what I do is I take the tail of negative v and put it on the tip of u. So I'll do that in red right here. And then from there, I go left 1 and down 4. Does that make sense? So left, let me get the right color here. Left 1 and down 1, 2, 3, 4. And notice it will look like an exact copy of what we have over here, except headed in the opposite direction. So let's be clear here. This is negative v here, whereas this was positive v right there, and in green this was u. And this is still a copy of u. So then remember what we did in the first one with u plus v. We connected the tail of u to the tip of v. We're going to do the same thing here, except it's the tail of u to the tip of negative v. And there you go. There's u minus v. So actually, I wanted to use this first drawing for something to convince you of how we add in component form symbolically. So let's use that drawing to convince you of how we add symbolically in component form. So for a second, let me go ahead and erase that guy. It's going to get in the way. Let me erase that guy. So let's examine u plus v here. And I think that'll give us a clue. So this vector in blue, what would, so notice the tip is right there. What would the change in x be, delta x, from tail to tip of the vector in blue? Just count. 1, 2, 3. Delta x is equal to 3. And then what's the change in the y coordinate? What's delta y from tail to tip? Looks like 1, 2, 3, 4, 5. Delta y is 5. Okay. Now compare that with the original vectors u and v. And what are we essentially doing? So first of all, in case I'm not clear here, u plus v in component form then is 3 comma 5, right? Okay. That's what I'm saying. So essentially what we're doing to get the component form of u plus v, what we're doing symbolically is just adding corresponding components, aren't we? Of u and v. So you add the 2 and the 1, you get 3. You add the 1 and the 4, you get 5. So, well, that's about as simple as you could hope for, right? So we can state that rule now. Let's state that rule symbolically. I need to define symbolically the vectors. So just to switch things up once again now, I'll let v equal, instead of ab, I'm going to call the components v1 and v2. And I'll actually state u first because I like alphabetical order, I suppose. And I'm going to let u equal, or have the components u1. So this is a subscript 1, u2. So it's just a way to generically, symbolically define u and v. Then you guys tell me, what's u plus v? Yeah, then u plus v, this is the symbolic definition, you guys. So you said u1 plus v1 for the first component, right? u1 plus v1, comma, u2 plus v2. So that's the symbolic way of saying what we just said, or what we just observed, actually. Okay, so that's a definition right there, isn't it? That's the definition of addition of two vectors, component-wise, right?